Hey everybody, I hope you're doing great today. We're going to go ahead and continue on with proofs today. So the idea with a proof, right, is this idea that we're trying to show through a series of intermediate steps how premises would entail a conclusion. So the idea is that each one of these intermediate steps should be something that's super innocent and trivial, something that's obvious that we can all accept. And so the point of what we're trying to do is we're trying to figure out what are those innocent steps. So last time, right, we started off by just doing this a bit intuitively and just listing out in English, right? If I know that A and B are both true, well, then it sounds like I should know that A is true. But the point is we then formalized that, right? We got very specific. So the idea is there's a specific rule called conjunction elimination, such that if you know that something and something else are true, then it's innocent enough just to say one of those things is true, right? Just to specify, right? If I have a dog and a cat, then it is correct to say I have a cat. It's not wrong to say I have a cat, right? And so that's what we want to do today. We're going to be adding more rules to our toolkit here, right? And the idea is all of these rules are just different ways in which these are different licenses for us to create new lines, to infer new things based on what we already know. If the premises say we already know X, Y, and Z, then based on that, what can we do with it, right? So just like, right, a carpenter will have a set of tools with which she can, right, manipulate and change the materials she's been given. You can think of the premises as the materials you've been given and these rules as the tools that you can use to work with those materials to get it to some sort of other product, right? How is it that those starting points really can yield that end point that we're talking about? So today we're going to be looking at how to eliminate conditionals and biconditionals. So if you remember from last time, we talked a bit about introduction and elimination rules. Introduction rules were those rules that allowed us to build new sentences with the connective in question, right? So if I wanted to convince you that you have a dog and a cat, the idea was, okay, just prove that you have a dog, prove you have a cat, and then you can prove, then it follows that you have both a dog and a cat, right? So conjunction introduction was as simple as it gets, right? If you know A and you know B, then you know A and B, right? So introduction rules are our ways of building up to new statements. Elimination rules are our ways of starting with statements and seeing what else would follow. Suppose I know I have a dog and a cat. Well, then it follows I have a dog, right? Or suppose I know that I'm both a professor and I'm right, and I live in Colorado, right? Well, then it follows. Suppose I'm a professor and I have a cat, right? Then it follows that I'm a professor, full stop. Or it follows that I have a cat, full stop, right? I don't need to list everything out every single time. That's all and elimination's doing, right? Or with negation elimination, right? Suppose I know it's wrong to say that I don't have a cat. Then it's right to say that I do have a cat, right? So all of these, the point is they should be very intuitive and very innocent on their own, right? There shouldn't be any situation in which you're like, I don't know if that's always the case. I don't know if I have a dog and I have a cat. I don't know if it's always right to say I have a dog and a cat, right? So the idea with all of these rules, right, is that they're very innocent, right? If you accept that you have a dog and you accept that you have a cat, it shouldn't be any surprise that you should accept you have a dog and a cat, right? We're not making any big jumps here, right? Each of these things is a very simple little thing. Because the point is, if we're able to show that the premises, through using only these really trivial rules, and the other ones we're adding here should be just as innocent and trivial, well then the conclusion just as innocently and trivially follows from those premises, right? It's just as strong as an inference as all of the inferences that led up to it. So today we're going to be adding more rules to our tool belt. So we're going to add another 4 rules, and specifically we're going to add the 4 rules for conditionals, right? How do we introduce them? How do we eliminate them for both conditionals and biconditionals? So let's start with an example. Suppose I have this argument here, right? I'm assuming that A leads to B. I also think that B leads to C. And further, I think that A is actually true. These are all the premises we're starting with, that we're supposing at the outset. You might already notice something that we've looked at way back when, right? If we zoom back weeks ago, this idea we called modus ponens. This was back when we were just differentiating for the first time between valid and invalid arguments, right? We were able to separate valid arguments from invalid arguments based on their structure alone, right? This was just what got us thinking about structure in the first place and what led us to wanting to build our formal language and that sort of thing. We already saw, look how good this structure was. That if we accept that A leads to B and A is actually true, well then sure we should accept that B is true. Right? I mean, look at how many examples we looked at, right? If you accept that if a person is human, then they are mortal, and you accept that Socrates is human, then you should accept that they're mortal. The only way in which Socrates wouldn't be mortal is if either he wasn't human, or if being human meant you're not mortal, right? And that's really what's going on down here again, right? When I say that A leads to B, but oh, look at this, A is actually true, well then what has to result is that B must also be true. Right? That's exactly the same form we saw above, right? We had if left, if purple, then red. Purple is true, therefore red is true. And that's all that we're doing down here. We're matching that exact same form, except now we're not just going to say, hey, it looks right. Now we're calling this conditional elimination, right? And we're getting that from lines 1 and 3. So that's the idea. Just like before, the only way that B is false is if either A wasn't true or A doesn't actually lead to B, right? And that's exactly what we mean by conditional elimination. We're going to say, if we have that A leads to B, or that phi leads to theta, and you know that phi is actually true, that A is actually true, then you know that theta has to be true. Right? That B has to be true. If you know that one thing leads to another and the one thing is true, then the other thing has to be true. The only way that that other thing isn't true is if either the first wasn't or the first doesn't really lead to the second, right? And we can look at this in terms of the truth table itself. The only way that theta isn't true is if we have either one or the other side not being true, right? If phi is true and if phi leads to theta is true, right? Then theta has to be true, right? The only way theta would ever be false is if either the conditional was false or the left-hand side was false. But if we have both the left-hand side and we have the conditional, then we are forced to say that the right-hand side was true, right? And none of this should be very surprising, right? I'm going back to the truth tables to help you see how this all connects. But like ultimately, this is already the sort of thing that we all saw in week 3. That if A leads to B and A is true, well then B has to be true. It's just that now what we're doing is we're giving it a name. We're calling this conditional elimination. Right? We're taking lines 1 and 3 and we're saying, okay, line 1 told me something led to another thing, and line 3 told me that something was actually true. So on line 4, I know that that other thing had to follow as well. And as soon as I do that, right, and as soon as we have this rule in mind, we should be able to see we have another application of this waiting in the wings. The thing to notice right away is to say, oh, okay, cool, I can do it again. Because now I can say, oh, on lines 2 and 4, I'm going to do another conditional elimination. Right? Because line 2 is telling me B leads to C. Line 4 is telling me B is actually true. Right? So it's again the same exact pattern. But now I just get C out. Right? So conditional elimination is just telling us if we have this conditional and we have the left-hand side of this conditional, then you get the right-hand side. So the way to be thinking about this is just the following. Right? You want to try to find, do I have anything that matches this pattern up top? And if so, that gives me the thing on bottom, right? So let's look at how this goes in our proof right here. We had if A then B, and A matches the pattern on top, and that's what gave us the B down below. And then we did just the exact same thing. If B then C plus B matches the pattern on top, and that's what gave us C down below. And now that we have C, right, if we had something that said if C then something else, we would be able to match that pattern again, right? But the point is we're constantly trying to fit that pattern itself. So it can be useful to see this right in another way. So I've built this application to help you see how the highlighting works in real time as you can change and do different things yourselves. And this argument here is very much similar to the one we were just looking at, right? We're trying to say P leads to Q, Q leads to R. I already know that P is true, therefore I think R is going to be true at the end of the day also. So what we're going to do is we're going to just do these conditional eliminations. So what I'll do is I'll just click conditional elimination. When I click one of these boxes, it'll tell me anything that would satisfy, right? Anything that could fit in there. So when I click my conditional box, it'll say, okay, here are the conditionals you can choose from, right? When doing a conditional elimination, you always need to choose some conditional, right? So if I chose if Q then R, and then I choose the other box, it's saying, okay, I'm only going to highlight what matches the left-hand side. But notice nothing over here actually matches that left-hand side. So nothing over here is going to be highlighted yet. Instead, if I do my conditional elimination and I choose the other conditional, now it does have something that'll match its left-hand side, right? What we call the antecedent. So now when I click that and I do an execute, look at that, I get Q out. And when I click Q, I can see the history of where it came from. What happened? Well, I got it from a conditional elimination on lines 1 and 3, right? I had this if P then Q, and I had that P was true, and that's what gave me that Q was true. And so then now on the next line, I can do another conditional elimination. So now I can select another conditional. So now in this case, I'll select if Q then R. And now when I click for the left-hand side, the only thing that would match that format is Q, right? P doesn't match the left-hand side of this conditional, only Q does. So when I execute it, right, it tells me I'm done because I've achieved my conclusion. But the point is, right, again, all that I'm doing is I'm just matching that pattern. I'm just saying, okay, I had this conditional, if left then right. I also had this left-hand side. That's how I got the right-hand side. So that's how we started the proof, right? We got Q because P leads to Q and we already had P. And then now that we had Q, we were able to do the next step. We were able to say, okay, now that I have Q and I know that Q leads to R, I can get R. So conditional elimination should really be pretty intuitive, right? Like the idea is this is what we meant by the conditional all along. We were just saying that this thing leads to that thing. So if you have this thing, you know you have that thing, right? That was the whole point of it in the first place. We were just trying to say this will lead to that. So if you have this, you get that. Doing conditional elimination is going to be a really popular thing. It's going to be come up with in a lot of proofs. So it's important to get really comfortable with this way of thinking about it in terms of pattern recognition, right? Just like a carpenter, right, isn't thinking every time she needs to use a hammer, oh, let me look up what the rules for a hammer are, right? The idea is you similarly want to internalize what the rules for something like conditional elimination are, right? It should be very intuitive, very obvious whenever you want to eliminate a conditional. What does it take to do that? What does it take to say, I already have a conditional, here's how I can get something out of it? So biconditional is then very similar because the only difference is now I can go both ways. So for a conditional, right, we were only thinking about it in terms of one direction, right? We were saying phi leads to theta. And so if you have phi, you get theta. Being 7 foot tall means you're taller than 6 feet. So if you're 7 feet tall, therefore you're taller than 6 feet. But the other direction doesn't work, right? Being 7 feet tall means you're taller than 6 feet. So if I know I'm taller than 6 feet, that doesn't mean I'm 7 feet tall, right? I could be 6'5" or something. Biconditional elimination lets us go both ways, right? It's like saying, if you're a triangle, then you have 3 sides exactly. If you have 3 sides exactly, then you're a triangle. It goes both ways. It's not just one direction. So the whole point is, if you find out that something has 3 sides, you know it's a triangle. If you find out something's a triangle, you know it has 3 sides. It's not like the conditionals that are only one direction. Biconditionals are 2 different directions. So in a sense, biconditionals are even easier than conditionals because it's just you don't even have to verify that you're looking at the right side. All that we have to do is just check, do you have one of the sides? So let's look at this particular example. Suppose I know that B is true if and only if A is, but B is also true if and only if C is. So if I know that C is true, does that mean I know that A is true? Well, biconditional elimination doesn't care about the direction. So I know that because C is true, and because C leads to B, then I know B is true. And why? Just because of biconditional elimination on lines 2, and 3. And now that I have B established, now that's just one of my materials, right? Now that's just something I can use. It's now a new building block to work with. Now that I know B is true, and I know B leads to A, right? This is going in that other direction, but it's still perfectly good, right? I know that A must be true. Why? Because lines 1 and 4, biconditional elimination, right? And then I'm done. I'm done with my proof again. I showed that assuming these 3 things really did lead to this conclusion based on just these very trivial, innocent steps. So let's look at an example in our program. So suppose we wanted to do a biconditional elimination, and I select which biconditional I want to work with. So suppose I choose this one. Well, notice how I don't have either one of the sides right now to work with, right? The left-hand side would be P, the right-hand side would be R. So in order for me to do a biconditional elim with line 1, I would need to have either P or R already out there, but I don't have either. What I can do first, though, is I can do an AND elimination, right? And I can take my R away from this guy, and now I have R on its own, right? I pulled it off of that AND. And so now what I can do, now R is just another one of my materials that I can use. So now I can do my biconditional elimination. I want to do my biconditional elimination on that. And then I need to decide, do I have the left-hand side or do I have the right-hand side? If I click the left, right, nothing matches the left-hand side of my biconditional. But clicking the right, no, I do have the right-hand side of my biconditional. I execute and I get my P, right? And right now the highlighting is off, this P should be red, but the idea, right, is that this P just comes from doing a biconditional elimination from R and P if and only if R. So next, after I get my P, I might be thinking, okay, let me do the other biconditional elimination on Q if and only if S. But again, just like before, I still don't have the sides for, I don't have Q and I don't have S, so I can't actually do that. What do I need to do first? I need to take off, I need to unpack for myself the other side here, S. So now I can do my biconditional elimination. I can say, okay, I've got if Q then S, I've got the right-hand side over here, that's S, and that's what gives me Q. And so now, look at that, I've matched what I need to match. So to finish it off then, right, I just need to get P and Q together, so I'm just going to do that. I'm just going to say, okay, my left-hand side, that needs to be P. My right-hand side, that needs to be Q. And so I execute, and I get P and Q together. So that's how this works, right? We're just, again, trying to fit the pattern of these rules, right? What materials do we already have? What rules can we use to give us new materials that allows us to use yet more rules? So let's look at this example here, right? Already these statements are getting kind of big and complicated and ugly. And as we go, and of course, like if we try to do this in any serious capacity, like in mathematics or computer science, they're going to get more and more complicated. So this is why it's going to be so important not to just rest on how obvious just the argument seems to you, and instead we need to really build our intuitions and really internalize the rules themselves and make it so that the exercising the rules themselves, that's what becomes second nature. So for instance, in this case, right, I see I have this conditional statement, I have this negated statement, and I have this atomic statement. So right off the bat, right, I want to think about what can I do with all of my complicated statements, right? I don't have an and, so I can't do an and elimination, a conjunction elimination. I might look here and I see, oh, you got this conditional, right? If either N or O, then L. But I can't do a conditional elimination. Why not? Well, because you don't have the left-hand side on its own line. But we don't have that. So what can we do? Well, one thing we can do is this biconditional elimination. So let's look at what we can do with these statements, right? I can't do a conditional elimination, right? Why? Well, because conditional elimination always needs two sides. It's like, here's your lock, but where's your key? You need to have that key on its own line somewhere, right? So you might be thinking, oh, well then why don't I just put this on my own line somewhere? Well, again, you can't put things on your own line somewhere until you've justified them, right? Until you've shown why we're allowed to put something on its own line somewhere. So let's think about what we're able to do with this proof, right? First things first, I can't do a conditional elimination because I don't have the left-hand side, right? It's like I have the lock here, but I don't have the key, right? Conditional elimination always needs the two parts, the conditional but then the left-hand side of that conditional, so I can't do anything with my premise 1 yet. I don't have any conjunctions anywhere, so I can't do like a conjunction elimination or anything like that. But I can do a negation elimination, right? Because these negations are sitting on the outside. These are the main this is the main operator followed by another one. So the first thing I can do is just simply n if and only m. Right? And this is just negation elimination from line 2. Right? And so now that I have this line, now I do have a biconditional statement. I didn't have a biconditional statement before, right? This is why it's so important to be able to recognize what's the main operator, and that's why we call these things, that's a negated statement. That's not a biconditional, it's a negated statement. The thing inside is a biconditional, right? So now that I have a biconditional, I can say, okay, cool. Now I can do my biconditional elim because I have my bicon and I have my right-hand side. So I can give myself n through biconditional elim on lines 3 and 4. Right? Now, so I've used my tool to produce some new materials to work with. Now, n is just one of my new materials to work with. Now, notice what can I do here? I want to be thinking ahead to do a conditional elimination, right? If I did a conditional elimination, well, the result of that would be L. That's my goal. So I need to somehow show that I need to somehow get N or O on its own, right? And some of you might have already been thinking ahead about how you might do this. That's why we were after getting N in the first place, because now I can just say N or O. And why? Why am I allowed to just add on this or for free? Well, because again, this is why it's so important to internalize these rules. That's exactly what disjunction introduction is all about. That's the whole point, is that I had N, and so I know if N is true, well then either N or O is true, right? That was the whole point, right? So down here, because I know N is true, I'm going to say, oh, well then I know either N or O is true, right? And all that this is just line 5. It's not from line 1. It's just from line 5 or introduction. I'm thinking ahead to use it in combination with line 1, but like, just be careful here. Why do I know that N or O is true? The only reason I know N or O is true is just because I know N is true. It has nothing to do with line 1. I only believe N or O is true because N is true. Why do I believe N is true? Because lines 3 and 4 tell me that N is true. Why do I believe lines 3 and 4? Well, 3 is a premise, so I accept that just at the outset. And 4 I get from premise 2. But none of this has to do with premise 1. I'm just thinking ahead for how I'm going to work with premise 1, because now I do have my setup for conditional elimination. So this is a very common occurrence, right? You might see a conditional that you know you're going to want to do an elimination with down the line, but what you need to do is construct somehow that left-hand side. It's like you have this lock sitting there for you, and what you need to do is build the key to do it, right? So now that I've gotten N or O from line 5, now I can use line 5, so I'll even do it like this. I'll put a blank here. I'll use lines 6 and 1, right? The left-hand side plus the conditional, that, through conditional elimination, is what gives me what? Well, that gives me L, right? Because it's just the right-hand side. Again, this is just this, it's just the same pattern that we were looking at before. And the point was we were just spending all of this time here just building that left-hand side so that we could do that conditional elimination at the end, right? We were building up to the point where we matched the structure that the rule was asking for. But to do that, we had to obey the structure of each and every rule as we went, right? We just did a very innocent negation elim. and then a very innocent biconditional elim, and then we added on the or. And right, the only reason we were adding on that or, right, the only reason we introduced it is because we were thinking ahead for how we wanted to do that next rule down below. So that's how these proofs will work, right? It's a lot of just looking at, okay, what patterns do I already have? And then what patterns am I close to that I want to try to manipulate, right? And I could use what I already have to manipulate certain things to make those other things actually work, right? So I had a near miss of a pattern, so I worked with all of these other ones until I could actually make that pattern perfect. And that's when I could actually execute the rule, right? That's exactly what we have over here. Okay, so now let's start to think. So that's our two elimination rules. If you already had a conditional or a biconditional, that's how you unpack them, right? That's how you squeeze out the information that they're giving you, right? That's how you utilize those assumptions or those things that you have. But suppose instead that you wanted to prove that a conditional was true, right? Suppose you wanted to prove, like in this case, that P really does lead to S. That if P were true, S would have to be true. And none of these premises say that explicitly, of course, right? Premise 1 tells me that P leads to Q. Premise 2 tells me that R is true. It doesn't even mention P or S. And then premise 3 tells me that Q and R lead to S, right? But somehow I want to try to justify why I believe that P really leads to S. And again, right, especially with these early examples, you might think it through intuitively. Well, P leads to Q. And if we already have R, that means we would have Q and R. And if we have Q and R, that means we would get S. But really, the way you want to be thinking about that intuition is try to think about that as a sketch for how you might go through the proof itself. But we want to slow down and really make this rigorous. What are all those steps you're making? So intuitively, right, we can see if we had P, we could see how we could get S. Intuitively, we know that P would lead to S, right? And that's the idea. Again, that's the whole point of the conditional, that P leads to S. So here's what we're going to do. In order to make these sorts of things clear, we're going to do them in a subproof, or we're going to be using these things called subproofs. A subproof is just a series of intermediate steps where we temporarily assume something that's unjustified. So we're going to temporarily say, okay, suppose P was true. What would happen? We make a temporary, unjustified assumption to see what follows, and then we discharge that assumption. We make an assumption, see what follows, and then step back to see what we've learned. What would the assumption have led to? That doesn't mean we're going to believe the assumption. It doesn't mean we're going to believe that the consequences of the assumption are actually true. But the point is we're just going to believe that this assumption really would lead to those consequences. So here's what I mean by that. What we're going to do in this proof is we're going to say, all right, assume that P were true. And we represent this as an assumption by indenting the proof, right? So we're going to mark this as like, okay, let's tell a story for a moment. What I'm going to say next is not guaranteed to be true. It's just a hypothetical. So the idea is I'm assuming that P was true. Now, based on P being true, well, it would follow that Q's being true, right? That's just 1 and 4 from a conditional elim, right? We just take 1, we take our assumption, and then it follows that, okay, Q has to be true. But then, of course, if Q were true, well, I already know on line 2 R is true, so then that means Q and R is true, right? That's just 2, 5, and intro, right? We're just taping those things together. But of course, because Q and R is true on line 6, and line 3 tells me that Q and R leads to S on line 3, that means just a simple conditional elimination tells me that S would have to be true, right? Based on line 6 and lines 3. As we zoom out then, what we say is, let's step outside of the subproof now. Let's discharge the assumption. So we're no longer pretending that it was true. But the thing is, we've learned something. We've learned that if you were to assume P, then it would lead to S, right? That justifies to us that P really does lead to S on lines 4 through 7. Not just 4, 7, but 4 through 7 in this rule which we call conditional introduction. So the idea is, I don't, right, after the proof is over, I don't believe P is true. I don't believe S is true. But what I believe is that P would lead to S, right? And that's all that we mean by this conditional. So the point of a subproof is to allow us to temporarily assume something, show what that would lead to, so that way we can take a step outside of the story and show, okay, here's the moral of all of that, right? If you were to say this thing, here's what would have to follow as a result. A couple things just to be clear here. We never end within a subproof. I never am going to end without that last line, because in a sense, that would be like saying, I haven't discharged my assumption. That would be like I'm pretending my assumption is still true, right? But the only reason like that it's okay to make an assumption is because we're being honest. We're saying, I'm not going to believe this the entire time. I'm making it temporarily. I'm going to dispense with this later. Because all that I'm doing is I'm just trying to show what would follow from it. I'm not trying to prove that it's true. I'm not trying to prove that P is true. I'm not trying to prove that S is true. I'm just trying to prove that P would lead to S. So we never finish our proof still inside a subproof, because that's like finishing your proof like inside a hypothetical story, right? You need to end your story and tell me, what is it that we really learned from this story, right? We only ever make assumptions so that we can discharge them and see what we learned by the subproof as a whole, right? We only ever set up subproofs to see what does this overall story tell us. So like once we're outside of the subproof, we never like point to a particular line in the subproof. We don't do that at all, right? All that we do is we only ever point to the subproof as a unit, as just here's a story where we showed that this assumption led to this conclusion. And we just accept that as something we should believe. But none of the individual pieces have we justified. So again, we didn't learn P. We didn't learn S. We learned that P leads to S, right? And it's this, right? It's this conditional structure that's so important here, right? That's why it's a conditional introduction. So the rule itself is just this. These lines here are meant to indicate that we've indented it, right? It's a bit hard to show, right, when we, based on this format, and there's no other lines to show you indentation from. But the idea is, this figure here is showing we're inside a subproof. And I started with phi, and then I have this ... arrow, and I landed somehow on theta. And so the idea is, if I could build a subproof that looks like that, then I really would have justified that phi leads to theta, right? Okay, so let's look at a particular example to see how this works. Suppose I have this argument, right? I'm assuming that P leads to Q. I'm assuming that Q leads to R. And I want to prove that P leads to R, right? Like this, I mean, again, we could go back to our intuitions. This seems like it should work, right? If P leads to Q and Q leads to R, well then, right, we could leapfrog over Q and we get to R, right? Like it seems like it cascades. But how do we actually justify that? I can't use conditional elimination, because as soon as I select a conditional, I don't have the left-hand side of either one of my conditionals. So I can't use conditional elimination. So what am I to do, right? Well, what I'm trying to prove is that I don't care that P is actually true. I also don't care that R is actually true. I'm just trying to prove that if P were true, it would lead to R. So what I'm going to do is I'm going to just do that. I'm going to say, all right, let's introduce a conditional. And so when I introduce a conditional, what I need to do is I need to select first, what is the thing that I'm assuming? What's my left-hand side? And the thing that I'm assuming, right, is it's the left-hand side of my conditional. I'm assuming P. I'm trying to show that if P were true, I really would get to R. So I'm going to assume P, and the thing I'm going to try to prove, it's not this, it's just R alone, right? I'm trying to show that P will lead to R, right? And so now that's what I want to do. So, right, here's the idea. I'm trying to prove that P leads to R, and I'm justifying that through this conditional introduction on lines 3 through 6, right? I already know how to justify this last line. How is it justified? It's justified by a subproof that starts on line 3 and it ends on line 6. And we can see that the start of it starts with P, and it should, right, this little italicized thing is giving you a hint, you really should end this with R. Because the whole point is you're trying to show that P really does lead to R. So when you set this up in this application, right, it gives you that structure itself. But if you're doing this on paper, you want to do the same sort of thing. You want to say, okay, if I'm going to do a conditional elimination, let me jump a bunch of space and say, okay, here's the conditional I'm trying to prove. And then what I'm going to do is I'm going to take that left-hand side and I'm going to put it at the top. That's the thing I'm trying to assume. Suppose that left-hand side was true. And then it's the right-hand side that you're going to put on the bottom, right? It's not the whole conditional that you put on the bottom, right? You're just trying to show that P really does lead to R. So you show that P, your assumption, really does lead to R, the end of the story. And then once you get to R, that's when you stop the subproof, you step outside and you say, see, P really does lead to R. So now our goal is to show, right, we need to fill in that subproof. We need to actually demonstrate how P leads to R. But it better have this structure. It better start with P and lead to R. Now our job is just to fill in those intermediate steps. And that's why it's called a subproof, right? Because that's essentially what we've always done in proofs in general, right? We have our premises, we have that thing we're going to, and we're just looking for filling in those intermediate steps. So now our goal, right, is just to think, okay, I need to get to R, I have P, and I have my premises. How can I do this? Well, now that I have P, I can do my conditional elimination, right? So here, right, let's go ahead and select our P as the left-hand side. And as soon as I select P as my left-hand side, I click my conditional, and that tells me, okay, the only conditional that matches that, if you're trying to do a conditional elim, is the top one, right? Your left-hand side better match the left-hand, or the antecedent here better match the left-hand side of the conditional. So I execute, I get my Q, right? And it matches that thing perfectly. And now I can do the same exact thing, right? I have my Q, matches the left-hand side of this conditional. So, right, we can do our conditional elimination again, because now we have this conditional here, and we have the left-hand side of that conditional, and so, of course, it's going to yield R. And as soon as we reach R, right, the whole point was that was the target of our subproof. So what we've shown, right, is that P really does lead to R. So the idea with conditional introduction, right, is that we just assume something, we show what it leads to, and then the result of that isn't that we believe either the assumption or the consequence of that assumption. It's just that we believe that the assumption would lead to that consequence, right? We don't believe P, we don't believe R, but we do believe that P leads to R. And that's the idea for conditional introduction. That's conditional introduction, and you might already be able to see, right? Biconditional introduction is going to be just doing that, but twice. Because all that we want to do for biconditional introduction is show that not only does P lead to Q, but also Q leads to P. So we could come down here for this example, right? Suppose I have this example that says, okay, suppose you know A leads to B, D leads to C, and A is true if and only if D is true. We're trying to show that A and B are true if and only if D and C are true. So how are we going to do that, right? Set aside what my premises are. Those are going to be important and useful, but I already know. As soon as I know that I'm trying to prove this biconditional, that I'm trying to prove to you that this is true if and only if that is true, I am going to set up two subproofs, right? I'm going to do this before I even really think about anything else, because I know I better have two subproofs if I'm going to introduce a biconditional. I better have one subproof that starts with the left-hand side and yields the right-hand side, right? This is how I show that if left, then right. But also, I better have another subproof that starts with the right-hand side and yields the left-hand side, right? If I'm trying to show that Ted goes to the dance if and only if Diane goes to the dance, right? Then I need to show that if Ted goes, well, then Diane goes. But if Diane goes, then Ted will go, right? I need to show both directions. So each one of these is essentially just a conditional introduction. You're just showing how one assumption would lead to one consequence. It's just that when you show it in both directions, that's what gives us both directions of the arrow, right? So again, this just comes down to exactly what we mean by the arrow, by the double arrow, right? And it's just that it's both arrows, or it's both directions of the arrow at once. So we started off with our example, just premises and a conclusion. As soon as I saw I was doing a biconditional as my conclusion, I thought, oh, okay, cool. I'll set up my two subproofs because that's how I prove that a biconditional is true. And now all I need to do is I need to just zoom into each subproof, right, one at a time. How do I prove, based on these premises and based on this assumption, that D and C would follow? And so that's all I'm doing right here, right? We say, okay, well, based on A and B, I can eliminate, right? I could do an and elimination, gives me A alone, right? And with A and premise 3, right? I know that's just a biconditional elimination that gives me D, right? That's just a perfect match of that pattern. A if and only if D. A is actually true, therefore D is true. And then, of course, line 7 is just a classic conditional elimination, right? You have D is true, but D entails C, therefore C is true. So now you have D and C, and so you can just put them together, and you've shown that, yep, assuming A and B really did lead to D and C. And so now what we're going to do is we're going to just stop that subproof. We're discharging that assumption, right? That's why I've left the space here, right? Doing this on paper, right? It's just classically important to make sure you like draw lines to say, okay, subproof has ended here or something like that. But the idea is now with our second subproof, we've set aside the original assumption, right? We're not pretending anymore that A and B is true. Instead, in the second subproof, we're going to pretend that D and C are true. And then, so based on D and C being true, I can get that D is true. Based on D being true and premise 3, right, I know that A is true. And based on 1 and 11, I can get B. So the point here is that when I'm inside this subproof, I can look at other things, like I can look at my assumption of the subproof, and I can also look at the premises of the argument, but I can never look at the other subproof, right? This was just a different story. So when you're inside a subproof, you can always look at, right, the premises that are outside of you, but you can never look at a different subproof based on different assumptions, because that's just a different hypothetical. This hypothetical is the one that shows us that A and B leads to D and C. This hypothetical is the one that shows us that D and C leads to A and B. But the only way that they do what they're supposed to do is if we're specifically assuming all and only what we're assuming, right? To show that D and C leads to A and B, we need to just assume that D and C is true and show that just based on that assumption, A and B follows, right? We don't want to assume anything extra. Okay, and now based on doing that, we've really shown that A and B is true if and only if D and C is true, right? Based on the first subproof and the second subproof, it follows that they both lead to each other, right? And again, I've highlighted the structure a little bit more over here again, right? We're trying to show that left leads to right, so we show that we're trying to show that left leads to right and right leads to left. So to do that, we show that left leads to right, right leads to left. Therefore, left is true if and only if right is true. Okay, so let's look at an example again in our program. So suppose I am trying to prove, right, that P is true if and only if R is true. And I know that P is true if and only if Q is true. And that Q is true if and only if R is true. So again, it might feel like, okay, like there's some, like, clearly, like there's this chain of things going on, just like we saw in the conditional case, in just the straightforward conditional case. But again, we need to slow this down. Can I do a biconditional elimination? Well, no, because I don't have either the left or right side of either of these statements. So they're like impenetrable in a sense right now. What I need to do if I'm going to prove this biconditional is I need to say, okay, biconditional intro. The left-hand side is P. The right-hand side is R. So then when it executes this, right, what we see is I have two subproofs. I'm trying to show that P is true if and only if R, so I have two subproofs. I have the one that says P leads to R, red leads to green, but also R leads to P, green leads to red. And so now my job is just for both of these just to jump in and think, okay, so how do I do just that subproof? How do I get from P to R now? And as soon as I fill in both of these subproofs, this last thing is going to be happy, right? It's already set up to where it knows, right, what the structure it's coming from is. It just needs you to fill in the details for how those subproofs are supposed to work. So first, what we need to do is we need to get from P to R. So what I'm going to do is just a classic conditional or biconditional elimination, right? So I'm going to go biconditional. Here's my biconditional. In this case, I have the left-hand side. That gives me the right-hand side, right? Similarly, right, now that I have Q, and I have if Q, then R, if and only if R, so then I can do another biconditional elimination, and then I get from if Q, if and only if R, and the fact that Q is true, then R has to be true. And then, of course, right, the next line is the start of our next assumption, because we've shown that P leads to R, and now we need to show that R really leads to P. So what we're going to do is just essentially the same sort of thing, right? Because I know that R is true here, right, I can do another biconditional elimination from this conditional and this right-hand side, and when I execute, I get Q. And so then, now that I have Q, right, I can get P finally, right? I can say, okay, so from biconditional elimination, from P and Q, and then I have the right-hand side, I can execute and I get Q, or I get P. So the point of all this is that we were trying to show if P is true, then so is R. And if R is true, then so is P. So that's all we did, right? We just started with we just had two subproofs. We showed if P was true, then R is true. And then we showed if R was true, then P would have to be true, right? And that's exactly what biconditional intro is asking for. It's asking for you to find one subproof that shows that the left leads to the right, and another subproof that shows the right leads to the left. And if you can do both of those things, then you've really shown that the left and right have to be true in exactly the same situations. So that's biconditional introduction, right? And it's essentially just doing conditional introduction just twice. And conditional introduction, right, that is just going to come down to whether or not you really understand what is a conditional in the first place. This idea that it's just saying, if something was true, then this other thing has to be true. So with all of those, right, we've added our next 4 rules into our tool belt, right? Now we know how to eliminate conditionals. If you had a conditional, then you just need to see, do I have the left-hand side? And if that's the case, then you can get the right-hand side. If you have a biconditional, then you just have to ask, okay, do I have either the left or the right-hand side already? In which case, you could get the opposite side. So that's how you would, if you already had a conditional or a biconditional, that's how you would squeeze out what they're worth, right? That's how you would utilize the information that they're giving you. Now, suppose you wanted to prove a conditional or a biconditional, right? That's where the subproofs come in. You would say, all right, I want to prove to you that P really leads to S. Let me assume that P was true just temporarily and show you that it leads to S. Or if I was going to show both directions, right, I would show P leads to S, and then S already also leads to P. So as you're doing this, what you want to be thinking of is, how could you apply your elimination rules to things that you already have, right? If you already had a premise that's a conditional, right, what would you need to find in order to do a conditional elimination on it? Or you want to think about your introduction rules for what you're aiming towards, right? If you were trying to prove somebody a conditional, what is it that you would need to set up in order to justify that conditional? But if you already have a conditional, you don't want to start building subproofs because that doesn't make much sense, right? You only build the subproofs to justify the conditional, to build it in the first place. Okay, so that's 8 out of our 12 rules. So at this point, we have a pretty strong proof system. We can prove a number of different things in our language. We can't prove everything yet. Just because something's valid doesn't mean we can prove it quite yet. But after next time, we'll be able to do that. So let's recap very quickly what we've learned today. First, we started talking about conditional and biconditional elimination. And conditional elimination was really just modus ponens that we looked at from way back when. This idea that if something leads to another thing, and you know that something isn't true in the first place, then you know that other thing would have to be true in the first place. And so exercising conditional elimination is really about just doing this pattern recognition, right? Just trying to find, do I have a conditional and the left-hand side? Oh, great, I can get myself the right-hand side. And then biconditional is really just a more lenient example of that, right? You don't have to care whether or not it's the left or the right-hand side. If you have either one of them, you get the other for free. So really, this is just building on the sort of things that we already have been, working with for weeks at this point. The real new thing here is just this idea of subproofs. This idea that we're going to temporarily assume something just so that way we can stop assuming it at one point and show what we've learned as a result for that. And as long as you can get on board with that, the idea of a conditional introduction is just the most natural or intuitive way of doing this. I'm going to temporarily assume that this thing was true, not because I actually think it's true, but just because I'm going to demonstrate to you what consequence would happen as a result. So I don't believe either P or S is actually true. I just believe that if P were true, then S would have to be true. And again, the biconditional is just doubling up on that, right? It's just saying, all right, if you want to show that P is true if and only if S is true, you need to show both directions. All right, that's it for today. Take care out there.